Hey everyone, it's Dr. Bianchi. I hope that all of you are doing well so far this week. We are getting through the semester and I hope everyone is hanging in there given this challenge that we're all going through and experiencing. I am recording this video at home in sort of my mock classroom here in order to help us make sure that we're on track with the new statistical tests that we started talking about over the past week. So this video is meant to be sort of a replacement for the typical in-person meeting that we would have on campus where we troubleshoot and walk through some of the problems together. So just a couple quick announcements. In order to do anything involving the t-test, you do need to have the t-table available. So that's a new statistical table that we're working with, and you can download that on D2L. I highly recommend printing it out. And you also want to have the new updated formula sheet that covers chapters 9 through 11. All of the formulas are organized there for all of the t-test problems you'll be encountering over the next couple weeks. The second part of our stats project is totally based on t-tests, and instructions for that will be up soon. But just to kind of get us going, over the past week, you should have been reading chapter 9, introducing the t-statistic, and hopefully you've already watched my full lecture video. I posted some practice problems that I wanted everybody to take a shot at that's going to count for this week's meeting and activity credit. And in this video, I want to kind of walk through the basics of the t-test and also go through those problems to make sure we're all on the same page. Let me just turn the light on here and see if this would make things a little bit better. Yeah, I think so. Okay, so the t-test. Before we broke off for spring break and before we left campus, we had only talked about z-scores, right? Z-scores allow us to locate a score in a distribution, and they also allow us to compare two different scores that come from totally different distributions with their own means and their own standard deviations. So we use the SAT and ACT example for a lot of that stuff, just showing that we can take two different results that come from two totally different places, and we can see which one is more or less competitive. We also talked about how with z-scores, we can determine whether an individual is significantly different from the group or not. So we had mentioned that z-scores above 2.0 and below negative 2.0 are basically grounds for saying that that case or that individual's performance is statistically different compared to the rest of the population. Okay, that's all review from before spring break. The t-statistic is another hypothesis test, another inferential statistic that we use in a certain situation. Okay, and the key feature of the t-test is that we use it when we lack details about the population. Specifically, we do not know the population variability or the standard deviation. If you'll remember with z-scores, we always were given all of that information about the population in order to compute a z-test. With t-scores and t-statistics, we lack information about the population standard deviation. We don't know what it is, and we have to use our sample and go off of just our sample data in order to test our hypotheses. Okay, so the function of the t-test is it allows us to test out our hypotheses when we lack critical information about the population. Now you'll remember samples are supposed to be good reflections of the population. And what we can do is we can use the sample variability to provide insight as to what the true population variability would be. So up here on my board, I have simply posted the t-statistic. Let me see if I can zoom this in just a little bit. Okay, this is our formula for the t-statistic, and our t-statistic is computed as t equals the sample mean minus mu, the population mean. And we're dividing by this new term here called the standard error of the mean, okay, SM. This is basically our proxy for the population variability or standard deviation, and it's called the standard error. We're going to use the sample information to compute the standard error. And the standard error is being used of the true population variability because we don't have that value. So computing the t-statistic is relatively straightforward, but you need to first calculate standard error. So whenever you are running a t-statistic, the first step is to get that denominator. What is the standard error? Okay, so let me just go ahead here, and I'm gonna erase my t formula really quickly. I don't have a ton of space on this whiteboard. I'm gonna try to get a bigger one. When we calculate the standard error, okay, there are two ways of doing it. And you can go back to the lecture slides and find this. You can also see it in the formula sheet. Okay, our standard error can be calculated using a standard deviation-based approach, which is the standard deviation over the square root of the sample size. Okay, that's one way to get the standard error. When should you use that formula? Well, if the problem gives you the standard deviation, easy enough, it's just gonna be plug and play. You're gonna put the standard deviation up top, and you're gonna do the square root of the sample size on the bottom, and simple division is going to produce the standard error. Now, we also have another way of doing this. Okay, and I'm just gonna write or. We can use the variance-based approach, which is the square root of the variance over the sample size. Okay, the square root of this whole chunk, the variance over the sample size. When should you use that approach? Well, maybe the problem that you're being given gives you the variance. So then you're going to use the formula that's easiest there, which would be the variance-based approach. Both of these are going to produce mathematically equivalent results. Okay, you can calculate the standard error by either using the standard deviation or the variance-based approach. Use whichever one makes sense in the context of the problem that you're given. Okay, now remember, the whole point of calculating the standard error of the mean, right, is to give us some idea of the real population standard deviation. Okay, we don't have information about the population variability. This standard error is a proxy for that. We're using the sample to get a good guess of how much variation there is, how much variability is present. Okay, and we call that the estimated standard error. We're using the sample to estimate what the population would be like. Okay, so there you have your standard error, estimated standard error calculations, all these formulas on the formula sheet. Let me go ahead and erase this. And what we're going to do now is we're going to go full circle through one of the problems that came up in the practice questions. So let me share my screen with you here. Okay. Okay. So these were the practice questions that you were supposed to go through and turn into D2L. If you haven't already, go ahead and do so. You'll still get credit for them, of course. With everything going on, I really just care that you're doing your best to stay on top of the material and turning in the assignments. Okay, I'm gonna go ahead here and skip to one of our full circle problems. Okay, this is a great example of something you might see on an exam. A sample is selected from a population whose mean is 50. Okay, note, we have the population average, but we don't have anything about variability. After a treatment is administered to individuals in the sample, the new mean is now 55. Okay, and the variance associated with this sample is 64. So let's just imagine, let me just put some context to this. Let's imagine that this is a study on individuals suffering symptoms of dementia, okay? And they are performing on a memory test. We know that the population average for individuals with dementia on this test is 50. Now we take a sample of people and we expose them to a treatment that we hope is going to improve their memory. And after they go through the treatment, the mean memory score is 55, okay? It's up 5 points from the population. The question is whether or not that is statistically significant. Can we be confident that that 5-point difference truly reflects a treatment effect, or could it be due to just random chance and variation? Okay, the whole point of running a t-test is that it allows us to tease between those two interpretations, whether we have a real treatment effect or whether this is sort of a chance kind of, lucky finding. We're given information about the variance of the sample, okay? The variance is 64. And remember, if you take the square root of the variance, you always come back to the standard deviation. Okay, so the standard deviation here is, right, what's the square root of 64? Right, 8. If you square 8, you get 64. So you can go back and forth between standard deviation and variance by either squaring or square rooting the value. Okay, now here is the question. If the sample has 4 scores, okay, that means we have 4 participants, conduct a hypothesis test to evaluate the significance of the treatment effect. Like all tests in this class, we're running a 2-tailed test, looking for extreme cases at both ends of the curve, and our alpha level, our risk of a type 1 error, is equal to 0.05. That is the most lenient value we can use, giving us a 5% risk of a type 1 error. Okay, that's going to be important for using the t-table here in a moment. Okay, so we're being asked to run the t-test and then back it up with a measure of effect size. Cohen's d is the most popular. Okay, Cohen's deviation is going to give us an indication of by how many standard deviation brackets did this group improve compared to the population. Measures of effect size give us a pure measure of the true magnitude of the treatment effect, not being influenced by sample size. Okay, so there's our problem. Give me 1 second while I just get some of these parameters up on the board, and then we're gonna walk through this together. Okay, let me stop my share here. Okay, so I just wrote some of the parameters up on the board here. Okay, the population mean on the memory test is 50. The sample after treatment scores a 55, okay, 5-point improvement. And the variability, okay, in this case, we're given the variance is equal to 64. What's the first step? We need to calculate a t-test. Well, if you'll remember, right, t is equal to the sample mean minus the population mean over the standard error. Well, step 1 is to get this value here, this denominator. Let's go ahead and calculate the standard error. I'm having to do a lot of erasing here because there's just not a ton of room available. Well, I'm going to go ahead and use our variance-based approach to calculating standard error because we're given the variance and it's just straightforward. Okay, so the standard error is equal to the square root of 64 over our sample size, which is 4. Okay, so we end up with the square root of 64 over 4. And that ends up leaving us with the square root of 16, right? If we go ahead and compute that, we get the square root of 16, which equals 4. Okay, our standard error in this situation is equal to 4. That is going to be the denominator of our t statistic. Okay, so let me just leave that up for a second. You can check it out or you can pause the video. Otherwise, we're going to proceed with filling in the rest of our t statistic. Okay, so we know that t is equal to the sample mean, which is 55, minus the population mean of 50 over our standard error that we just calculated and was equal to 4. Okay, so we end up with 5 over 4, right? 55 minus 50 is 5. 5 over 4 is 1.25. Okay, so t is equal to 1.25. That's our sample t statistic. The question now is whether this is statistically significant. Can we be confident that the 5-point improvement on the memory test actually reflects the impact of the treatment? How can we figure that out? Well, this is where the t-table comes in, because we need to compare our obtained t-value with the critical value provided by the table. This is where that degrees of freedom thing comes in. Okay, degrees of freedom, it's very complicated to explain this. It's one of the more complicated things to explain in statistics. I'm going to keep it simple for everybody. It's just going to be a necessary kind of calculation for us. Whenever you're asked for the degrees of freedom, it's just the sample size minus 1. Okay, so degrees of freedom equals n minus 1. So if we had 4 participants in our study, 4 minus 1 is 3. Okay, our degrees of freedom in this problem is 3. Okay, that's important because it's going to tell you where to look on the critical t-table. So for any problem where you're dealing with a t-statistic, in order to get your degrees of freedom, you just subtract 1 from the sample size. Let me go ahead and share my screen with you now. And I am going to pull up, let's see. Just give me 1 second here. Hit share. Okay, let me pull up the t-table. Okay, here you can see our t-table, and you should have this available. Now, we're always going to be running a two-tailed test at the 0.05 level. And I can make this a little bit bigger. So I encourage you on your own t-table to just kind of circle this. And you're always going to be using this column here. Okay, some students will just do a big circle around this entire column because that's almost always where we're going to be looking, at least for my questions and some of the questions on the exam. Now, you may get questions in MindTap that ask for the 0.01 level of significance, and then you would be using this column. Okay, but whenever you're given the alpha value, okay, in this case, the problem was a two-tailed test at the 0.05 level, we're going to be referring to this column here. Now, we need to match that up with our degrees of freedom, and we've already identified that we have 3 degrees of freedom in this problem. So I'm going to scroll over to the 0.05 area, and you can see here our critical t-value is 3 and change. Okay, 3.179. So our value that we got was 1.25, but the t-table is saying that our t-value must be greater than 3.179, or it must be lower than negative 3.179 for us to have a significant result. Okay, let me go ahead and draw this for you. Let me just show you what this looks like. So we've used the t-table to find the criteria. Okay, it's basically telling us what we need to outbeat, what we need to compete against in order to have a statistically significant finding. Here is my t-distribution, okay? And basically the table is telling us, right, at an alpha level of 0.05, meaning that we're taking the most extreme 2.5% of cases in one tail and the other, combined 5%, we split it up across both tails, okay? The extreme 2.5% here, or the extreme 2.5% here. Our sample needs a t-statistic falling in the critical region in order for us to reject the null hypothesis and say the treatment did in fact work, it significantly improved memory scores. What the table is telling us is that the boundaries, okay, for these critical areas are positive and negative 3.179. So our sample needed to exceed 3 and change or fall below negative 3 and change for us to say the treatment worked. Now our t-value is 1.25. That's somewhere in here. Okay, getting a result in here supports the null hypothesis. The null hypothesis says the treatment doesn't work, it doesn't have an effect. So in this case, we fail to reject the null hypothesis. We cannot rule out the null. We cannot say confidently that this treatment has a significant impact. That 5-point difference may just be due to chance factors. Okay, we fail to reject the null hypothesis. There's not enough evidence that the treatment worked. Okay, we did not get the t-value that we needed. Okay, so there is our hypothesis test. Now we want to back it up with a measure of effect size. Effect size tells us, does this treatment have any promise? Okay, now let me just unpack this a little bit. When we hypothesis test with a t-statistic, sample size plays a really, really big role. Now we had a super small sample. 4 people is really, really small. I doubt many of you would trust too much research that only samples 4 people. Very, very limited sample size. And it's possible that our t-test was underpowered. Okay, in chapter 8, we talked about power, right? Do you have enough power to run your math, to run your statistics? And one of the biggest influences on power is your sample size. Do you have enough people in the study to pick up on a treatment effect if one did occur? It's possible that this treatment is promising, but that we just don't have enough participants in the study. Effect size measures like Cohen's d allow us to figure out if it's worth recruiting more people or pushing our research further because there might be something interesting that we're failing to capture. Okay, so Cohen's d for a single sample t-test is very easy to calculate. Okay, it's simply going to be the standard deviation. Okay, and we are going to, let me see here, find my problems here. I'm getting this wrong really quick. Got this flip-flopped. Okay, Cohen's d is super simple. Okay, the numerator is the same as the t-statistic. It's the sample difference compared to the population. And then we divide by the standard deviation. So we know that there's a 5-point difference between the sample and the population. What's our standard deviation? Well, in the problem, we were given the variance, right? The variance was 64. If we square that, we get back to standard deviation, and we have 8. Cohen's d is equal to 5 over 8, which is equal to 0.625. 0.625. That is our Cohen's d value. It's moderate to strong. What does it mean? What is that number actually saying? That number is telling us that in this study, okay, looking at a group of people who come from a population, right, that experiences dementia, we know the average score on the memory test was 50. Right, 50. But our sample scored a 55. Cohen's d is telling us that our sample shifted over a half a standard deviation bracket above the norm. Okay, so they moved 0.625 standard deviation brackets above average. That's a pretty significant effect size measure. We have moved these participants, we have improved their memory by over half of a standard deviation bracket. Pretty impressive. What that tells us is, hey, let's go back out and let's recruit more people to be in this research the second time around, because if we amp up our sample size, we may just get a statistically significant result. We may just find that this treatment does work if we have the power and sample size to back it up. Okay, so effect size can allow you to determine that something interesting is going on when you have a small sample size. Let me show you how to write this up in APA style format. This is going to be important for the statistical analysis project that will be up later this week. We ran a t-test, okay, with 3 degrees of freedom. The result was 1.25. It was not statistically significant, so the probability of a type 1 error is greater than 5%. Okay, had it been significant, we flip the sign, the probability of a type 1 error would be less than 5%. But it was not significant. Okay, and then Cohen's d, this could all go on one line. Okay, I'm just going to do it on the bottom here. Cohen's d was equal to 0.625. Okay, you could ideally write that as one long string. All of our statistical letters are italicized. Okay, and that is kind of the APA string of terminology that you would write up. Underneath it in regular words, you would say something like a single sample t-test was conducted on the data. The results were not statistically significant. We cannot rule out the null hypothesis. We just simply do not have enough evidence that this treatment is significantly effective. However, our measure of effect size was moderate to large, quite promising. Perhaps we would increase our sample size the next time we do this research. Okay, so there I've gone through an entire problem, okay, walking through a one sample t-test, calculating measures of effect size like Cohen's d, and also writing it up in APA format. Now what I want to do is I want to go to the next problem in the slides, and this is just going to show you how important sample size really is. Okay, so let me go ahead and pull that problem up. Okay. Okay, we are going to work together for this problem as well. Okay, I want you to actually do this problem or check your work again. Okay, but here we have a sample. Everything is staying the same here except sample size. So it's the same study. Okay, the population average is 50. After the memory treatment, the mean is 55 for the sample, and the variance is 64 for the sample. But our sample size is different. Now we have 16 participants. So go ahead and run a single sample t-test on this sample. Make a statistical decision. Is the correct response to reject the null hypothesis, or do we fail to reject the null hypothesis? And then calculate Cohen's d to measure the size of the treatment effect and interpret it. Okay, please take a few moments to work through that, or at least review your math, and then I'm going to walk through it here on the board. Okay, please feel free to pause the video if needed. Okay. So first step is standard error, SM. This is going to be the same approach we took in the previous problem. We're given the variance, so we're going to use the variance-based formula. So the square root of 64 over the sample size, which is now 16. Okay, this ends up giving us the square root of 4. Let me just switch here. The square root of 4 is equal to 2. Wow, we have cut our error term in half just by increasing our sample size. Now we're going to be dividing our t-statistic by a smaller number. That's going to give us a larger t-statistic. Larger t-values are more likely to be significant when we use the table to make that decision. Our standard error is equal to 2. Okay, let's fill out our t-statistic. T is equal to 55 minus 50, so it's 5 over our standard error, 2. We end up with 2.5, right? So our t-value for this sample is 2.50. Is that statistically significant? Do we have a significant result? Well, what's next? We've got to go look at the table. Okay, here we are at the t-table. We are conducting a two-tail test at the 0.05 alpha level. Okay, 5% risk of a type 1 error. But our degrees of freedom is equal to sample size minus 1. So 16 minus 1 is 15. So I am going to scroll down here to 15 degrees of freedom. And if I go over here, I find my critical value of 2.131. Okay, that's the critical value. Okay, we find our degrees of freedom of 15 and we scroll over to the 0.05 column. 2.131 is what we need to beat out. We have a 2.5, so many of you might already know the correct answer here. Okay, let me go ahead and draw this one out though, just for visual purposes. Here's our t distribution. The top 2.5% of the tail is marked by a t-score of 2.131. The extreme 2.5% in the lower end of the tail, a negative 2.131. Well, our t statistic is 2.5, so we're right in the extreme tail. We can reject the null hypothesis. This is an extremely unlikely result if the treatment didn't work. This is an extremely unlikely result if the null hypothesis is true. Put differently, it's more likely that the null is wrong. The treatment had a statistically significant impact. Our t statistic exceeded the critical value. We can have confidence that this treatment does have a significant result. Had we gotten a value in here, we would fail, be unable to reject the null. Having values in the extreme curves, we can reject the null. Now, some of you might be wondering, why would we be doing a two-tailed test looking for a potential result down here? Whenever we test out a treatment or a new therapy or any kind of intervention, we have to be open-minded to the fact that therapies and treatments don't always improve people. They can actually also make people worse. So there have been famous examples of different kinds of programs over the years, like DARE, maybe some of you remember DARE from school, Head Start interventions, some different things that intuitively sounded like they would work. They sounded like, sure, that's a great idea, how could that hurt? But research has shown that they've actually had negative outcomes on health, education, and so on. So two-tailed tests allow us to test for the possibility that a treatment can both improve as well as hurt. And we look at both possibilities. Okay, here we have a significant improvement. Okay, let's go ahead and calculate Cohen's d. Remember, Cohen's d is not influenced by sample size, so it should stay the same. D is going to be equal to the sample mean difference compared to the population, which is 5 points, and we're going to divide by the standard deviation, which is 8. Okay, the square root of 64, the variance is 8, and we get 0.625. Okay, that number shouldn't change because it's not impacted by sample size, medium to strong effect size. Now, what I want to demo here really quick, I just want to show you how to calculate that other measure of effect size, the percent of variance explained, R squared. You may have seen it. R squared is the amount of variance or the amount of a result that our treatment can explain. So in this example, there's a 5-point improvement in memory, and the question is how much of that improvement is due to our treatment. R squared will give us that percentage. Super easy to calculate. R squared is equal to the t value that was obtained squared over t squared plus the degrees of freedom. Okay, that's all in the formula sheet, and it's just simple plug and play. So our t statistic, right, was 2.5. So we have 2.5 squared over 2.5 squared plus our degrees of freedom, which is 15. Okay, take a second there to calculate that. Let me pull out my calculator here really quick. Okay, so 2.5 squared is 6.25. Okay, let me just add 15 there. So we end up with 6.25 over 21.25. Let's go ahead and throw that in. 6.25 divided by 21.25, and we end up with 0.29. Okay, we can round to the second decimal point here. So r squared is equal to 0.29 or 29%. What does that mean? That means our treatment accounts for just under 30% of the improvement. The other 70% is due to other factors, time, mood, the people, things we didn't study or measure. But our treatment explains 30% of the improvement. That's what R squared is telling you. How much of the puzzle, how much of what you are trying to explain was explained with your treatment or your intervention. A lot of things influence people's behavior. You're not ever going to have a treatment or an intervention that explains 100% of something. So this is actually a pretty strong measure of effect size. It syncs up with what we got for Cohen's d. So here we have a statistically significant result. Now that we upped our sample size, our t-value was significant, and our measures of effect size are strong. How would we write this out in APA style? We ran a t-statistic with 15 degrees of freedom. It was equal to 2.5. The probability of a type 1 error was less than 5% by definition because we rejected the null. D equals 0.625, comma, R squared equals 0.29. Okay, so it's always your t-statistic. Was p greater than or less than 0.05? If it's less than 0.05, we rejected the null. If it's greater than 0.05, we failed to reject the null. And then we back it up with our measures of effect size, Cohen's d and R squared. Okay, both strong measures of effect size. So this is how you calculate a single sample t-test. Okay, if you are having any problems with these questions, please email me or post to the discussion board. Okay, you want to make sure you're following the formulas accurately. You want to make sure that you're doing the math accurately and that you're making the correct statistical decisions using the table. Now, what I want to do here is just introduce the next version of the t-test that we're moving into looking at this week. Okay, we're looking at 3 versions of the t-test in this course. One version is the single sample t-test, where we're using one sample of people to test out a prediction. But sometimes in research, we have more than one sample. Maybe we want to compare 2 groups or 2 samples to see if they're different from one another. Maybe we treated them differently. Maybe we put them in an experiment where one group was exposed to one manipulation and the other group was in a control group. Okay, so when we want to compare 2 groups of people, we need to use the independent samples t-test, where we have 2 independent samples and we want to see if they are statistically different from each other. So when we run our 2 sample t-tests, we have sample 1 and we have sample 2, and we're looking to see if they are statistically different. Now, you'll see all of the formulas for the 2 sample t-test on the next page of the formula sheet for chapters 9 through 11. This is all covered in chapter 10. Same concept, same process of hypothesis testing, where we're going to calculate a t-statistic and use the table to make a decision about whether the groups are different or not. But the math is a little bit different because we're going to have to take into account both groups. In a sense, the independent samples, the 2 samples t-test, is just doubling up on everything from the 1 sample test. Okay, you're going to have to calculate a standard error value, you're going to have to calculate a t-statistic, and you're going to have to make a statistical decision. What you should do now, if you're all set with the one sample test, is start reading chapter 10 and be sure to watch my lecture video where I cover in depth the 2 sample t-test. Next week, I'll have another video just like this one where I walk through solving some 2 sample t-test problems. Okay, I hope that this video has helped. I think this is a good addition, a good substitute since we have lost our in-person meetings. I'm going to be making a lot more of these computational videos now that we're getting into more of the advanced testing. And I am encouraging you to please ask questions if you're confused, and please stay on top of the reading and my lecture videos. I will be posting the stats project part 2 soon. It's just going to be running some t-tests on the data, and I'll explain how to do that. I'll probably make a separate video for that. But for now, you should be wrapping up chapter 9 and moving into the 2 sample t-test, one of the most common statistical tests that we use in the behavioral sciences. Okay, I hope everyone is doing all right and hanging in there. I am here to help you if questions come up. Please do not hesitate to reach out. I am being flexible with deadlines. If people need me to work with them, just let me know. We are just trying to get through the semester as successfully as possible. Okay, otherwise, I will see you all soon, and I hope that you have a great day.